Hello, hello, and welcome to this RMetS meeting, which is celebrating 100 years of meteorology at Imperial College. Obviously, we would have liked to have seen you all in person in our lecture theatre, as we have welcomed so many of you over many years. But things are as they are, and so we are in the virtual world. Curiously, what we're celebrating is Napier Shaw's appointment as the first professor of meteorology was 1920, and I just looked up, which turns out was in fact the fourth wave of the Spanish flu. So there we go. History can repeat itself. So I've got a couple of slides I just wanted to share with you before we start. So we have the RMetS logo. Oh my goodness. There we go. So just a reminder, many benefits from becoming a member of the RMetS, a whole range of career support, professional stuff, but also information like a copy of weather, lots of discounts for conferences, journals, apps, shopping, lots of reasons to become a member. So please do become a member if you aren't already. So the program today, we've got a stellar list of very distinguished people with association to Imperial. So we'll start with Joe in a minute. And then we also have so Brian Hoskins, we have John Marshall from the MIT, and then we have Edward and Helen who are with us in physics now, actively working. So I'm sort of ahead of schedule. I think one thing to remind you of how you actually interact. Unfortunately, we're not going to be able to do it in a way which we'd normally like. So you're going to have to ask your questions into the chat. So you put your questions in the chat, and then the idea is that at the end of each talk, we've got 5 minutes, and I will ask the question to the speaker, and they will hopefully respond. So if you have questions, please put them in the chat, and then you can put them in during the talk. You don't have to wait at the end. So if there's something that comes to mind, just bring it up immediately, and we'll monitor them, and then I'll read out the questions. Hopefully, I'll be able to read out all of them, but we're sort of on a tight leash, so I might need to just select some. But we will try and answer all of them since we know who asked them in some form. There will be a recording of this as well eventually, so that will be on YouTube, so you can all watch it all again if you want. So I think we might as well get started. So we'll start off with Joanna. She's going to tell us about meteorology in South Kensington. Thank you, and enjoy the session.
Well, thanks, Ralph. It's great that you've organised this meeting, and isn't it a shame that we can't all meet up to have a view and a reminisce? But anyway, it looks like a very popular meeting, so that's fantastic. So I'm just going to set the scene, really, talking about the places where some of this science and activities took place, and also some dates and some people. I'm not going to say too much about the people because I'm aware that others in talking later will be on more detail of their science and what they achieved. So I'm just really going to mention people as a sort of historical record and their positions. So just as a bit of background, so before this meeting discussion is meant to start in 1920, I'll just give a little bit of what was going on in South Kensington. Back in 1851 was the Great Exhibition in Hyde Park, and you can see there the Crystal Palace, which was set up to raise money in order to develop South Kensington for science and cultural activities. And after that was developed the Natural History Museum and the Natural History Museum came later. The V&A and the Science Museum came. And then we had the Royal College of Chemistry and the Royal School of Mines moved from central London. Then the Normal School of Science, which became the Royal College of Science, and the City and Guilds. And Imperial Institute was built as a museum for the Empire, essentially, as an exhibition for the Empire. So here's a map dating back to 1914, and you recognise the geography, I expect. We've got Queensgate on the left, going north-south there, and Exhibition Road on the right. We've got the Imperial Institute Road going across the middle, and Prince's Gardens on the right. And you'll see the V&A down there, bottom right. And you can see little slivers of Science Museum across the middle and up to the left. So when the Imperial Institute was built, and here's a picture of it at the time, it's an absolutely massive thing. You can see it's fronting onto Imperial College, Imperial Institute Road there. Of course, the only bit of it that's left is the Queen's Tower, which you'll all recognise. And that's set up to do these displays of goods for the Commonwealth, essentially, and the Empire. So the Royal College of Science building was established in 1906, and Imperial College was created in 1907. And in 1910, the post office was rebuilt to house the Met Office on its upper floors. So there's the Royal College of Science, and you can see that's a drawing down there on the left. So it's facing the Institute across the road, and it must have been quite impressive walking down that road and seeing one of those buildings on the left and one of them on the right. If you look at the Royal College of Science, you'll see still bottom left there is a little bit still existing building, but most of it's gone. But the post office for this talk is of course the most interesting, and that's just sitting there, and you'll recognise the building. It's been a post office until relatively recently, and it's not just arbitrary that it was chosen to house the Met Office, because of course what with the wartime generation in networks and telegraphs and messaging across Europe, they needed somewhere to provide that, and the Met Office was providing the meteorological information, and the Post Office was providing the networks. So there they are sitting together at that point on Exhibition Road. If you go today and look at the building that was the Post Office, it's now the Dyson School of Engineering. You can see the front door there. And intriguingly, if you look inside the front door, I can just, here, there's the front. This is a picture taken very recently. You can see it still says Meteorological Office, and I think that's quite entertaining that they've left that there as a sort of record of the building's history. So what's going on in the department? I've put Hugh Longbourn Callender in here. He's not a meteorologist, but I wanted to include him. He comes into the story a little bit later. He's head of the physics department at Imperial for 30 years. Interestingly, he also invented the electric recording thermometer. You see a picture of it there with the recording disc drum underneath there. And he did thermal physics research amongst lots of other stuff. But another reason for having him in this talk is that he was the father of Guy Stewart Callender, who you may be well aware was the first person ever to relate increasing measures of carbon dioxide to increasing global temperatures. So he had some responsibility for meteorology, even if it wasn't a personal one. So if we look, still before 1920, but I'm setting the scene here, what's going on in teaching meteorology before 1920? It was just taught in the aeronautics department. This is the third year undergraduate syllabus for aeronautics. And you can see down here that meteorology is a small component of the physics course. Now, clearly, there was a great growth in aviation during the war, and the need for meteorology was boosted, and so the teaching was needing to be increased. And in 1920, the Air Ministry supported a new school of meteorology at Imperial College as a sub-department of the aeronautics department. And Napier Shaw was the first professor, quotes, only professorship of meteorology in the British Empire, I think it said then. With him, so he came from the Met Office, and with him he brought Elaine Austin, who was a professional meteorologist, to help, and also two people who were enrolled as visiting lecturers on the course were David Brunt, and we'll hear a lot more of him later, who's working at the Met Office at the time, and also C.T.R. Wilson, who you'll be well aware was the Nobel Prize winner for inventing the cloud chamber, a Nobel Prize 1927. So let's see what they were teaching. I hope this is not too pale, but this is a meteorology syllabus when the department first opened. And this is a postgraduate course for students from aeronautics, physics, and also the Met Office. And you can see the topics, and you can also see the lecturers. So that as a broad course, at the top there, we've got instruments and observations with Napier Shaw and Elaine Austin. And then we've got weather maps and forecasts by the same people. Physical and dynamical meteorology with David Brunt. Atmospheric electricity with CTR Wilson. And then more information about the atmosphere with Napier Shaw. So you can see it was a pretty starry cast list of lecturers, and the students then were getting a pretty good deal. So in 1924, after 4 years as Professor Shaw retired and Elaine Austin went back to the Met Office, so Imperial College decided to review how meteorology was going as a department. And it set up an external review panel. And this consisted of, Shaw was on that, and Callender, who I've already mentioned. Also, Richard Glazebrook, who was the head of aeronautics, who had been at Cambridge in the National Physical Laboratory, and he'd just come to aeronautics in 1920. And then Simpson, who was the Director General of the Met Office at the time. And they were set up to review what was going on in meteorology and advise, what should happen next. So they recommended that meteorology was continued as a PG subject, and also there should be some introduced into the undergraduate syllabuses of aeronautics and physics, that there should be more observations, meteorological observations made, and could be made from the roof of the physics department. And also Met Office staff could attend the lecturers without having to pay any of the college fees. So you can see they also looked at the expenditure, and on the right there you can see the total expenditure for all this added up to about £1,250 per year. So that was pretty cheap, I reckon. Anyway, this was all going very well, and so by the end of that decade, the sub-department of meteorology and aeronautics moved to the old Huxley building with the maths department. And the old Huxley building is this here on Exhibition Road, that's now part of the Victoria and Albert Museum. And you can see it sitting here in this map. It says Royal College of Science, and that's where meteorology and aeronautics went to. So in 1924, Gilbert Walker took over as Professor of and Head of Meteorology. He came from the Indian Meteorological Department, and I know Brian's going to say a lot more about him. In 1925, the University of London accepted meteorology as eligible for the BSc, so now you could actually get a degree in meteorology from the University of London. Just after that time, the first manual of meteorology was published, written by Napier Shaw and Elaine Austin. They'd started it during the war, but it was just published in 1926, and that became a major handbook for all working in meteorology, both in academia and at the Met Office. But 1932, the Met Office wanted to expand, and it decided to close its South Kensington office. Aeronautics moved to the City and Guilds building, but meteorology stayed in the Royal College of Science as a sub-department of physics. So just out of interest, here is the City and Guilds building, this massive great building on Exhibition Road, which is where now the business school and the mechanical engineering departments are sitting. So you can see this huge amount of construction that went on over that period to house science and engineering in South Kensington. Oh, I included this picture. It's not relevant really to Imperial College, except it includes some of the people that are in the story. And in particular, we have, you can see, I hope, Miss Austin, Elaine Austin. She's third from the left at the back there with a rather splendid hat. And number 16 at the bottom of the tree is Gilbert Walker. And then you've got Napier Shaw in the front with the hat on his knee. And other meteorologists of note in this meeting that took place in Germany in 1927 is L.F. Richardson, who's at the back, above the person wearing number 20, and also Willem Bjerknes, who's at the front with his legs crossed. So that was quite an interesting meeting going on, and obviously Imperial College scientists were very much involved in that. So Gilbert Walker retired in 1934, and at that point David Brunt, who had been a visiting lecturer, left the Met Office and came to Imperial as a professor and head of the meteorology department. He'd previously, before the Great War, he'd worked in solar physics and statistics, and so he was very clued up on meteorological observations. And he'd also been working in atmospheric conditions for chemical warfare, which is pretty unpleasant sort of thing to be working on. But leave that for there. He wanted to create at Imperial an institute for meteorology because of the growth of the subject, which was supported by the head of the physics department, but rejected by the university or the Senate as having no academic merit. Great. Oh dear. Right. But anyway, the college obviously thought it was a good idea because they put some money in, obviously seeing the signs of the times in order to expand the UK provision in meteorology, which was needed for the wartime activities. So in 1939, there was an independent department of meteorology, and P.A. Shepard, whose name I think was Percival, but he was always known as Peter, joined the department as a reader. There was an experimental hut set up in Harlington, and at that point, Imperial, together with the Royal Meteorological Society and the Air Ministry, bid to the University Grants Committee and succeeded in getting more funding. And this really opened the doors for an expansion in the topic. After the war, Imperial opened Silwood Park as a field station, mainly in biology, but also in Met observing. I should say that during the war, Brunt and Shepard went to the War Ministry and also set up the Met Office Meteorological Training School. So there was a number of appointments being made at this time. In 1946, Eric Eady joined as a student in maths, and he's a dynamical meteorologist. I'm sure you'll hear more of him later. And the person who became Sir John Mason, B.J. Mason, joined in cloud physics. He came with no experience in meteorology at all, but he knew about experimental physics, having lectured at Manchester. But he establishes himself as one of the leading cloud physicists. And then we have here Dick Scorer, who came in 1949, and Frank Ludlum in 1951, and I'm sure you'll hear more about those later in the clouds discussion, both of them leading cloud physicists from completely different angles. So in 1952, Brunt retired, and Shepard took over as head of meteorology, where he was there for nearly 20 years. And other people who joined during this decade included John Green, who came as a student, and he stayed on as an academic until 1986, and I'm sure you'll hear more about his work from John Marshall and others. They decided they needed some oceanography, and so they employed Henry Charnock in 1958, but I think he probably only stayed a year or two, so he wasn't a long-serving member of the department. I wanted to talk a little bit about radiation work, because I think nobody else in this meeting is going to be talking much about radiation. So back in 1954, the college appointed Richard Goody, who of course is a world leader in radiation studies, writing the first major textbook. He was only at Imperial for 5 years, from 54 to 58, but he had a huge influence on activities in science, in measurements, in instrument development, and in theory. So I think I put Bob Pearce there, but I didn't mean to put Bob Pearce. I meant to put Bill Roach, sorry. So he worked with Bill Roach at Silwood Park. They developed an emission spectrometer, which could see the spectra of gases previously unknown resolution. And here's an example from a publication in 1957 of an atmospheric spectrum made at Silwood Park from the emission spectrometer. And you can see it's there across the thermal infrared, looking at the emission And you can see signals from all the different gases in this so-called window. So that was a real advance in the science there. Also important, very important to us, is Ken Bignall, who came as a student in 1960s, and he did his PhD. This is a little bit of his PhD here, and he did experiments at Silwood Park, trying to get very, very long path lengths, horizontal path lengths. But in the end, he realised that one of the better ways of doing it was to set up on the Huxley balcony along a path cell that he could do multiple paths and get hundreds of meters of path to his absorption studies. And so he was able to make really interesting, innovative measurements of the water vapor, and in particular what's called the infrared continuum. So in 1963, we had the Linstead Review for the Robbins Report. That is of all the universities in the UK. It's a bit like the REF in those days. So I'm sure all the universities were cringing. But Imperial was graded A in civil engineering, meteorology, geology, mining and metallurgy, and B in all other subjects except history, at which they scored a C. So much for meteorology not being an academic subject, tee-hee. But the Robbins report recommended the expansion of Imperial College, and so meteorology was safe for a while. And in the 1960s, they took on some impressive PhD students. I've included a couple of year groups here. You might recognise the one in 1967, perhaps you can recognise Martin Miller and Mitch Moncrief on the back row there. And then in 1973, on the front row at the right, you've got Glenn Schutz and Alan Thorpe and Alan Gadian. So some really top meteorologists were training here. But for various political reasons, partly due to the growth in meteorology across the country, and also the fact that Reading University was almost next door to the Met Office, the department was diminishing, and the Met department closed in '75, and the group moved to the new atmospheric physics group as part of physics in the new Huxley building. And I'm sure John Marshall will tell you more about what it was like to be there. So I'll finish just saying thank you to a few people, Anne Barrett for providing some materials. Ken, of course, I mean, it's such a shame Ken can't be speaking at this meeting because he'd be able to do it far better than me. And he's provided a lot of interesting material, both online and in bits of paper and things. And perhaps we'll be able to exploit him to come and talk to us at a later date. Also, Hannah Gay's History of Imperial College, and a report written by P.A. Shepard, which is quite interesting on the history of the department. So I'll finish there.
Thank you very much, Jo. Gosh, what a way to start. That puts us all to shame. So, questions. So we got a question in the chat, but I'm not sure it's completely fair on Jo. So I wonder if other people have any information, please do add them to the chat as well, because it's a tough one. So Jo, the question is, how does this fit in? And I guess the question came up in the early part of your talk, I think, when you were talking about the really early days. How does this fit in with what's happening in the rest of the world? Was the UK the first to include meteorology as part of a degree?
I think not, but I don't know. Sorry, I'm afraid I don't know. Well, I'm not a historian, I'm just mugged up on this for this particular meeting. Well, I found it quite interesting what I've learned. And I will be interested to find out more about Europe and the rest of the world. I think there was a lot of activity in India. You see, Gilbert Walker was working in the Indian Meteorological Service before he came to Imperial, but I'm not sure about the academic courses or anything that were available.
Yes, somebody's just put it, I think, yes, so I think Germany, a lot of actually Imperial catch-up was all about catching up with Germany and doing formal science and engineering. So no surprise there that Ed pointed out that there was some early in Leipzig and places like that. So certainly things happening, but yes, thank you. So I just noticed, Jo, in your one of your things, it was talk about when you had this curriculum, it said physician, or was that a misspelling of physics? I don't know if you go through your slides.
Oh, what does it say?
Well, I thought it didn't say physics. I thought it said something else. So,
Oh, I probably got a typo. Sorry, I did miss.
no, it was the original document. It's one of those things where you scan the. I think.
Oh no, there was a typo. Yes, I know there was a typo in one of them. I think that's not my fault.
There's a fault. I was just wondering if it was a curious term for something, which.
No, it said physic-can instead of physical. I think it's just a typo. Do you remember typewriters, Ralph? Perhaps we're too young.
So it's okay. There's a. You just got it there.
Well, physic and dynamical. I'm sure that N's meant to be an L.
Oh, okay. Interesting. Yes, what a stellar list of.
Yeah, I know.
They charged them too many fees in those days, but yeah, great. I don't see any. Are there any other questions? I don't think we've got any others.
Well, I can be let off and enjoy listening to other people now.
You can be let off, but I have to say, generally, I'm so pleased that we're going to have a recording for all of this. I think maybe this is going to be a blessing in disguise for our meeting, because I think it's a fantastic record we'll have to share with the rest of the world forever. So we'll definitely put a link on our website as well. So maybe if we can use the time, Brian, if you're ready, maybe we can move on to Brian. Is that okay?
Fine, thank you, Rob. And yes, I was feeling a little trepidation anyway about this talk, but having had the talk from Joe first, she knows so much more than I do about what happened, and secondly, I see some of my dates are quite approximate, which is maybe like some of my numbers are always a bit approximate, I don't know. But anyway, so I'm sure there's many people listening who know far more about many aspects of what I'm talking about than I do, and I'd be very keen to hear afterwards about where I've got it wrong and what they know far more than I do about this. But anyway, my task is to talk about dynamics, atmospheric dynamics in the first 50 years, but there's going to be a bit of repetition with Joe in terms of actually putting the names up. And whether or not they're too much associated with dynamics, I thought I should mention them. So when we go to the first one, it shows, well, first, if I was giving this talk live, I would not show you the picture at the bottom under Napier shore. I would let it emerge, but anyway, you have it what it is. I didn't dare try and get it emerging gradually. But as we've heard, Napier Shaw was the first head of department. I saw that he'd actually been a reader in meteorology in the University of London in 1907. He really was a key figure around. He was in natural sciences in Cambridge, and then got very involved with the Meteorological Committee that ran the Met Office, and it was next door, and I think he probably took under some readership. But anyway, he was then in charge of the Met Office as part of his role there with the Meteorological Committee. And I put a few things. He was only 4 years, the final 4 years of his career at Imperial. And I put a couple of things, some of which aren't necessarily associated with his time at Imperial, but I wanted to mention them anyway. When Shaw went to the Met Office, he found a total absence of any research going on, and he dragged then Lemford from his old natural sciences in Cambridge days across, and they worked together and did some research. And one piece of work published in 1906 shows that it's entitled The Life History of Surface Air Currents, and it really is a superb picture way before the Norwegian model of what this surface cyclone looked like. And it showed the discontinuity lines for the wind, which later became, in the Norwegian model, part of the fronts. So it's very much the surface situation, but it really was a really good start on what the cyclone looked like, taking just surface data. So that was Shaw. I mean, as an expert in many areas, he really was a world figure in the subject. And he wrote, and I've got slightly different dates for the end of this, but he wrote this manual of meteorology because there wasn't anything to teach the meteorologists around. And it came in 4 volumes. And actually, when I was doing my PhD in Cambridge, these volumes were around in one of the libraries I could visit. And I just found them absolutely amazing. They showed great learning and some interesting aspects. And from one of these, volume 3, I picked up something which I later put in a paper. So volume 3 is the physical processes of weather. And he had in that a picture which I then borrowed and made this into this. There's the North Pole over here and the South Pole, the equator on the right, and the sloping surfaces are isentropic surfaces. And he talked about the underworld as being all these isentropic surfaces which are in contact with the surface of the Earth. And the overworld is then all the isentropic surfaces above there. And I found this idea really attractive. These are the surfaces where something that happens at the surface of the Earth can change, just be moved isentropically along this surface. And I later put in the middle world, which is the layers that cross the tropopause, and added it to that. But if you turn it upside down, it's a bit like the ventilated thermocline of oceanographers as well. So I found that extremely useful, and I think the dynamics was there. There's no doubt Shaw will have brought dynamics to the teaching he did at Imperial. So if I go on to the next slide then. So Gilbert Walker, we've heard, took over. Now, he was a mathematician, a Cambridge mathematician again, and expert in time series analysis. And in the great British tradition, knowing nothing about meteorology, he was the obvious man to send to India as in charge, well, mostly in charge of the observatories there. And he obviously took to this, and he looked around at what was going on in India, and it was failures of monsoons that was the big thing. There'd been a major failure of the Indian monsoon. And so using his expertise, he looked at relationships around the world in pressure to the monsoon and its possible failure. And this is where he came up with the Southern Oscillation, the pressure field, global pressure field, which later was seen to be associated with the El Nino phenomenon in the ocean, and we have the El Nino Southern Oscillation. So after his 20 years in India, then his last 10 years of his career, he came to Imperial College as the next head of department. And he continued his studies, although I don't know that anything's really appeared, of the yearly weather and climate, and also the mathematical theory of bird flight. I mean, I gather from in his undergraduate days, he was known as Boomerang Walker because of his studies of the flight of a boomerang, and he also very interested in the flight of birds. And I don't know whether I should include this in the RMetS thing, but that was the dynamics that seemed to be turning him on at the time. And then if we go on to the next slide, we come to David Brunt, who I saw described as the first full-time professor of meteorology. I don't know whether that meant he came into the office every day of the week, and the others came in only once or twice when they thought about it. But anyway, that was him. Now, again, the background, extremely important, as Joe has said. And it shows the wartime flavor that a lot of meteorology has, I think. The World War I, then, he was very involved in this chemical warfare, the atmospheric conditions associated with really gas dispersal near fronts, near the fronts over in Europe where the fighting was going on. Now it's interesting actually that on the other side of the lines was Jakob Bjerknes, Wilhelm Bjerknes, who was a professor at Leipzig and then got into describing again the movement of gases, and later then back in Bergen then came on we get the Norwegian cyclone theory. So on both sides there were these investigations of how gas was moving around. And some of his later work on the theoretical understanding of fog dispersal, again the boundary layer, the details of the boundary layer, its motion, its stability. And the stability aspect then, the Brunt-Weisler frequency as we know it, independently discovered, so I'm just told by Brunt and Weisler, giving the stability of the atmosphere. So the dynamics is there. It's not pure dynamics as we might know it now, but there's a lot of interesting, and the interest in the boundary layer coming in there. Now I put 4 people on this next slide here, all associated with this sort of period in which Brunt, I think, was building up the department. And as Joe said, Peter Shepard then came in 1939 and his background again was Porton Down, and he got into then the boundary layer motion, and that was his great expertise in terms of boundary layer physics and dynamics. and that's what he worked on for many years. And one of his students then was Henry Charnock, whose thesis was on turbulent wind over water. And Joe says he returned for a year or so later on to the department. Richard Scorer then, who was variously in maths, meteorology, and back in maths again. And I put two things opposite his name in terms of dynamics. One was the gravity waves downstream of mountains. And this is where his real lasting claim to fame, the Scorer parameter. I don't think he called it that, but I suspect he was quite pleased it was called that. The parameter he used there, which described whether the gravity waves propagated vertically or whether they were trapped. And that was clearly an important dynamical contribution there. And he moved very strongly to looking at air pollution again and dispersion. Frank Ludlum, I'm not sure whether it's 49 or 50, my dates, I trust Joe's far more than mine. And you may be slightly surprised I'm putting him in. Cloud processes, we'll hear about that later on. He was there with radar, and then the Wokkingdom Storm with his student Keith Browning and also Dave Atlas, who was visiting. And this really links to what I think is real dynamics, his conceptual models of cumulonimbus airflow. And he was very much, although the cloud physics was behind him there, very much a believer in that the air motion was incredibly important. And he introduced this concept of looking at a steady state, and so this propagating storm in a steady state with the airflow being extremely important. And I've even put John Mason's name down at the end there. Not most people's dynamicist, but I think like Frank Ludlum, he was very much a believer that the dynamics is incredibly important. And I think that was influential in many ways. I put these people down on the same page, and I'm talking about dynamics, atmospheric dynamics, but I think one of the interesting aspects of the department is the personal dynamics was not always very positive. We had some real prima donnas here, not Frank Ludlum, I don't think, but the others, and their interaction was not necessarily almost always of the most positive, I think. But they were major figures in Imperial, in UK, and in the world. So now if we come on to this later period then, so Eric Eadie. Eadie was, again, a Cambridge mathematician. He was in the wartime in the Met Office as a forecaster, and I suspect he was not very keen on this seat of the pants rule, go by the rule book of what the forecast will be. He clearly wanted to understand what these weather systems were, and he filled loads of notebooks with his ideas on this, and then he gave up the Met Office and decided to go to Imperial College to actually write down his ideas in the form of a PhD thesis, and I suspect he was very much welcomed there by Brunt again. And he wrote his PhD thesis in 1948, The Theory of Development in Dynamical Meteorology. There still is a copy of this, a pencil, of his pencil written PhD thesis. He wrote by hand three copies, and one of these is still in the physics department. Actually, it's in my locker at the moment in Imperial College if I ever get back there. But Rolf and Arno Chaya have kept this safe for many years. And it's an amazing thesis. It has 53 chapters. 53 chapters. It has no conclusion, and it would never get past someone, any examiners these days. But the first chapter is the gem, I think. It is a sort of tour of what he thinks Eadie thought was important in meteorology and where it was going. And I mean in one of my retirement jobs to really pull that out and tell the world about it, because many of those things have come in some form afterwards. But the thing we all know about from that thesis is the Tellus paper that followed on long waves and cyclone waves. And this was Eadie's version of how these waves exist. There is not a single reference in that paper. Again, you'd never get away with it now. And of course, in 1947, Charney had published his theory. It's not clear how much Edie actually knew about this, certainly not when he was writing his thesis. Certainly didn't get instantaneous communication in those days. And Edie's thesis then, his ideas of baroclinic waves was this sheared flow in the vertical with a constant density between a boundary, a surface boundary, but then also a rigid lid. And he found that that situation was unstable and that the waves that grew looked a lot like the cyclones, or certainly in the linear limit, he could be related to the cyclones that grew. And that was a major advance. And Edie went to Bergen to discuss his ideas, and he went to Princeton, and I know later to Stockholm with Rossby there. In Princeton, for instance, I know he met Joe Smagorinsky, and Joe Smagorinsky, some 20 years later, told me of how impressed he was with Edie and how he just thought he was just such a great meteorologist, great dynamicist. And in the early 50s, he was really doing some fundamental work on the general circulation and the role of eddies. And the Toronto proceedings of the Royal Meteorological Society, the centennial proceedings in 1950, contains a great paper there. He really didn't write much, but when he wrote it, my goodness, it was worth reading. Now, Edie had 2 PhD students that I know of, and one was Bob Pearce, Robert Pearce, and I'm not quite sure the date he came, but about 51. He came as a, well, his interest in meteorology was actually again back to the wartime, where as a teenager he'd been enrolled in taking meteorological observations, and that whetted his appetite. But I think his degrees were in mathematics. But then he came to Imperial College in the days of Brunt to work as a PhD student under Edie, and his PhD was on calculations. Note the word calculations. This was using computers, of the sea breeze circulation, and the work was published in 1955 in the Quarterly Journal. And that seems to have been quite a landmark thing on sea breeze circulation and the use of computers to do the calculations. And Bob Pearce, the other thing, he years later when he was at Reading, he did work on energy, on energetics of the atmosphere, but Herbert Real visited Imperial while Bob was there in the late 60s. And from that, Bob thought about the parameterization of tropical convection. This was one of the things he'd taken on, was numerical models of the atmosphere, whether it be to do with weather or climate. And he was thinking then about the problem of parameterization of tropical convection. And he came up with the interesting idea, very much Kelvin's circulation theorem, that you can have a circuit. If you watch my fingers moving around, think of a circuit in the upper atmosphere, or in the atmosphere away from the surface, and the circulation on an isentropic surface around that circuit is conserved. So he said, well, you can have all this up and down motion in convection, but it doesn't matter. All that matters to this motion around this circuit is whether the circuit expands or contracts. So it got away from all the details that some people were thinking about in terms of all the details of the convection. How much did you really need to know about that in order to parameterize it in tropical convection? And then the last one I'm going to mention, of course, is, as far as I know, the second student of Eric Edie, John Green. And John, I think, joined in about 55. I should say Bob Pearce left to be the second head of the Department of Meteorology in Reading in 1970. John Green, though, stayed for some time. John then took on, as a student of Edie, and I think he, in many ways, took on the mantle of Edie. Edie had become a perfectionist. He was a perfectionist. He found it very difficult to communicate with others around him, and he found the messy atmosphere. He'd almost gone as far as he could with his pencil and paper, and he really became someone that was very difficult to communication with others. And this was a characteristic of the later part of his life, which ended tragically as well. And John Green then took on the mantle of Edie. He actually took on the copious notes that Edie had written. And in fact, just sort of a personal note, when in the 1970s, Adrian Simmons and I were doing things on baroclinic waves, we always knew we were getting on well if John Green said to us, Edie did that. That was a sign we were on the right track. So we never knew what was really in those notes, but I think some of it did really come out in John's later papers as well. So baroclinic instability, John did a very important thing in his thesis there, which he wrote in this 1960 paper. There was real confusion because Charney, in his model, had a lower boundary, an infinite atmosphere with a decreasing density, and a beta effect. And he got these cyclone type waves. Edie had no beta effect, no decreasing density, and had an upper lid. And he got cyclone waves. So what John did in his thesis, again using numerical methods to actually solve the problems, he then essentially took the Edie model and then added beta effect and moved the upper lid and had decreasing density. And the ingredients were there that then Charney and Stern could come along with their criteria for baroclinic instability, where you could see the bits that Edie had originally and the bits that Charney had and how John Green had put together. And in fact, the long waves, which are slightly destabilized Rossby waves, are often known as green waves these days from his thesis. I put a second paper, which I love too, Green, Ludlum and McIlveen, which again was very much the steady ideas of Ludlum and thinking on an isentropic surface, so a sloping surface, gently sloping surface, and about relative to the system, what the air was doing. And the anticyclonic gyres you get there, I should have a nice diagram here, which I don't have, really look quite like the thunderstorm model that Ludlum had, but on this gently sloping surface. And that was a really nice bit of work there. But again, the steady state assumption and the relative flow of the atmosphere as crucial ingredients. And finally, John in 1970 published really his following on the mantle of Edie, where he was looking at the general circulation and the eddy transfers by these mid-latitude eddies, and how by mixing the quasi-conserved variables of potential temperature and potential vorticity, it maintained the westerlies in middle latitudes against the frictional damping of those westerlies. So that was a really great paper and wonderful dynamics there, continuing many of the traditions of Imperial College. So that's all I was going to say on that, except the other thing is through this period here, this later period, there were many good PhD students starting in the 60s and through to the 70s. And that's when I first knew the people at Imperial College, about 1968 or so, I think. And some really good PhD students. And I think my talk really leads on to there where John is going to follow. We're talking about that really fertile ground in which many meteorologists developed through their PhD program at that time. But I'll finish at that point. Thank you.
Thank you, Brian. So you mentioned that we were keeping the memories of Edie and his notebooks. I'll just point my camera to what's left of the Imperial College library. Not much, as you can see. I just picked books that are genuinely old and genuinely. And actually, as you were saying, I was just picking up this rather interesting thing, and it's the papers written by Gilbert Walker, which now open the first page has got a stamp of Imperial College of Science Technology. I don't know if people can see it, but it's dated March 1926.
Wow.
And in this is a compendium of all of his famous papers. And you said he was interested in time series. So it's like.
Okay, yep.
some sketches, and I saw another one, and lots of these, written and so forth. But I was pleased to see, when you look at it, there are a lot of correlation coefficients.
Yeah.
So things we haven't moved much. If you think about how often we see correlation coefficients in these days, it's okay. Now we've got EOFs to be really fancy, but yeah.
He was a serious time series analysis man. Yeah, statistical analysis, and he did a good
You'd
job.
be doing machine learning now.
I think he was very disappointed that his correlations with the Indian monsoon didn't turn out well in the subsequent years. And what's been clear in later years is during some decades they seem to work well, and other decades they don't. And I'm not sure anyone's really explained that. Maybe that's random, I don't know. But he was quite disappointed by that, I think.
I think it's not random. It's once you've published it, it disappears. That's the rule of thumb, I think. I think he would definitely be interested in machine learning nowadays.
Yeah, I think so, yeah.
So
I'm not sure he wanted to get his hands wet in the atmosphere too much, but anyway.
So great, thank you for that, Brian. So we got a slightly off-topic question, but there's a new meteorology entry, and he was wondering whether you could advise a book on dynamic meteorology.
Oh,
what's your
great.
favorite book on dynamic meteorology? Doesn't have to be related to Imperial, of course. What does Brian Hoskins recommend?
Oh gosh, I'm on a hiding to nothing here. I've got all sorts of friends that will never speak to me again. I think if you pick up any of them, you'll do fine. There are many, and I'm about to try and produce a second edition of mine, but that's when you've done your graduate and postgraduate degrees, you might find that useful too. So you've got a bit of time to get to that one. But I'm not going to lose any of my friends by saying pick up those, I think. But if you look at Wallace and Hobbes, you can't go far wrong as a starter.
Oh, here we go. He picked one. There you go. So Wallace and Hobbes, highly recommended. Any other questions before we move on? Don't see any. I noticed some interesting comments on. I don't know if people are looking at the chat. There was something about Charnock. So James Crease said. Charnock told me Scorer was challenged by a member of the public, so he did talk to public, to dissolve cumulus from the rooftop of the department by staring at them for a few minutes. He obliged.
I don't know if that's in the style of Canute to prove he wasn't that powerful or what, but anyway.
Well, public understanding of science, that's great. So thank you very much, Brian.
You're welcome, thank you.
Much appreciated. So we're moving on to John. Are you ready, John? There we go. John's ready. So I'll hand over to John Marshall.
Well, good afternoon, everybody. I'm coming in from Cambridge, Mass, where I live, and I'm a professor at MIT. But in my formative years, I was a student at Imperial College, and I arrived as an undergraduate in 1973 and ended up staying until around 1990 or so. I started as a grad student in the atmospheric physics group in physics, and then became a member of the faculty in physics. So I'm going to describe how I got involved in meteorology, the people that inspired me, and the research themes that influenced my work and many other people's work. So it's a personal account I'm going to give, and it's a period of transition from a freestanding department of meteorology that we've heard about, set up in 1920 and that we're celebrating today, and from that freestanding department into physics, into an atmospheric physics group within physics. My comments are not going to be comprehensive, but I'm going to touch on key points that I think that are relevant. Now, as an undergraduate in physics, I had no particular interest in meteorology, but we did take some maths classes over in the magnificent Huxley building that Joe showed us, and here's a photograph of it. And this housed the Department of Mathematics on the bottom 2 floors of the building. And it was there that I came across John Green for the first time, who would have a huge impact on my life. He was teaching an unusual applied maths class in which we'd attempt to solve problems live during class. And I remember vividly some of these problems. You know, one was, imagine you had a plank and you're walking down a bend in a right angle corridor. What's the longest plank you could get round that corridor? And so, you know, you could think about abstracting the plank to a line and perhaps doing it in 2 dimensions. But he wanted us to do it in 3 dimensions, maybe have a finite size plank. And John and a group of assistants would be clambering around across benches, trying to help us out. I just loved it. And it was a little bit frightening, but also great fun. And so I like the way John thought and expressed himself. He spoke like an ordinary person. He didn't use jargon. And yet it was clear that this ordinary person was a very unusual thinker, a bit off to one side, a bit strange in some ways, but that appealed to me. So I applied to do a PhD with John. And if he'd have been an astronomer, I would have studied astronomy. But it turned out that John was a meteorologist. And of course, as we've heard from Brian, a student no less of Eric Eadie. And the top 2 floors of this Huxley building housed the very eminent department of meteorology. So when I joined the group in 1976, it had already moved to the new Huxley building next to physics. And I realize now, I think more so than then, that the move represented a kind of an end of an era and a somewhat uncertain future. I think people must have been anxious and apprehensive that the physical space occupied in the new Huxley building next to physics was not as extravagant as the old building, with its 30-foot high ceilings and rooms within rooms. But of more significance, I think, the autonomy of an independent department had gone. I wasn't that aware of this at the time, but looking back on it, it must have been a major event in people's lives. But as a new graduate student, I just found it an exciting time. And I knew almost immediately that this was the kind of science I wanted to do. And over time, I learned something of the post-war imperial greats. So these are some of the people that we heard about. I don't have time to talk about all of them, but I do remember Frank Ludlum, the eminent cloud meteorologist. Frank was right at the end of his life. He died in 57, only 57 in 1977. But I remember taking a class from him on convection. And it was then that it kind of dawned on me that the endeavor we were involved in, it wasn't just about applied maths and computation. You know, when he spoke, you felt that some of the romance of the field, that he was in love with clouds. You thought he was a cloud. And I remember him once saying, any old fool can get the air up. It's getting it down again that's the problem. And many years later, I worked on the reverse problem in the ocean. It's easy to get water down it's easy to see how water gets down into the abyss from, say, polar convection, but it's getting water back up to the surface, which is the challenge. And that's been a recurring theme of my work in oceanography over the years. Of course, another person I heard about was Eric Eadie, subliminally at least. He'd only been dead 10 years, But his greatness was always there in the background and somehow reached into the future. And he represented the kind of pinnacle of the kind of science we aspired to do. You know, artful simplification applied to important problems, elegance, transparent mathematics exposing the basic mechanisms. And you know, Imperial was the place where we learned how to do that. Dick Scorer, I remember talking often with Dick Scorer, who Brian spoke about, and he was in applied maths, and I would go downstairs and talk with him. At that time, actually, he was mainly involved in Labour Party politics, but he said something to me that I always remembered. He said, you know, to discover something, you don't sit there at your desk waiting to be struck by lightning. You know, what you do is you get up every day and you try to do science, and you know, if you're lucky, something interesting will crop up. You'll discover something. So I might add, you know, that every dog has his day, and if you put the time in, you can discover things. And you know, these characters around. But so as I began my graduate work, most of these great scientists that we've been hearing about were gone. Yet the group was vibrant. There was new young faculty, lots of students around, masters and PhD students, and there was a very good feel about the place. This is a photo taken on the patio of the physics building. Ken Bignall would take these shots every year, and it's from the first year of my PhD students in the fall of 1976. Lots of students. There were master's programs and graduate PhD students all mixed together. And so I'm on the bottom right there. In the middle, on the back row, you can see Joanna Haig, who was a master's student. Of course, she went on to do her PhD at Oxford, coming back onto the faculty in atmospheric physics in the mid 1980s, and ultimately becoming head of the physics department. So what kind of research were we doing? So I'm going to review briefly these kind of research themes that we're all working on. And the first was analytical and numerical models of convection and clouds, and that we had young lecturers. I'll show you photos of them soon. Martin Miller, Mitch Moncrief, and they were studying atmospheric convection. And this work had its origins in the observational studies of Ludlum in the 1960s of tropical cumulonimbus and squall lines. So as Frank showed, if you go into the frame of the storm, then you could kind of assume a quasi-steady state. And Mitch set up analytical models of these systems. And alongside, Martin was building numerical models of convection. Martin was a student of Bob Pierce and had, with Bob, had developed numerical models of convection. Now I've grouped together a short list of people at the bottom. For example, Alan Thorpe and Roger Bruce. These I will return to these people in a moment, but you know, there were little subgroups working on these various themes. A second big broad theme that we were working on was zonally averaged models of climate, and this stemmed from John Green's famous paper from 1970 on the general circulation of the atmosphere. And by assuming that weather systems mixed potential vorticity, we could capture both heat and momentum fluxes, and in particular, upgradient momentum fluxes which sustained the surface wind pattern. So here's an analytical model of the surface winds, and once you know the surface winds, you can infer the direction of the frictionally driven overturning circulation. So the Andy White was very much involved in these in these studies and was a key person. Myself, Jeff Vallis, Wu was a grad student working with us too. The third theme of the work that was going on was thinking about low frequency variability of the atmosphere, and particularly atmospheric blocking. And this was motivated by the persistent drought of 1976, which plagued Europe, particularly Italy. And Green wrote a little paper in Weather in 1977, where he thought about some of the dynamical considerations of the drought. And this led to a whole slew of work, Ludovica Ilary, Glenn Schutz, working on diagnosing and trying to understand the dynamics of low frequency variability. So these were the themes that we were working on. And here's a picture of the people that I interacted with. Now, I'm sure I am sensitive to the fact that many people, perhaps people looking in, were there at the time. But I'm confining my remarks to the people that I interacted with on a daily basis. And of course, it's not really just about research. It's more about the people. And there was John Green, of course. Here's Martin Miller and Mitch Moncrief. These are pictures taken from the late 60s. And they were lecturers in meteorology at that time. There was Ken Bignall who we've heard about from Joanna in his work in radiation. Ken was a fantastic teacher working with master students, and he helped me a lot in my early teaching career at Imperial College. There are also senior researchers and postdocs, Andy White and Glenn Schutz, later of the Met Office. There was Alan Thorpe, who became a professor at Reading and ended up running ECMWF. And there were fellow PhD students, Roger Bruges, Ludovica Ilary, myself, Jeff Vallis, and Guosheng Wu. Rogers had a long career in meteorology at Reading. Ludovica became a scientist at ECMWF. We got married and now both work at MIT. Lotto is actually downstairs watching the proceedings over the web now. Jeff Vallis also moved to the US, but is now back home and a professor at the University of Exeter. Guosheng Wu is a very influential meteorologist in China and head of the Chinese Academy. So the research kind of hinterland was very rich. It was good for students. Lots going on, which was not directly related to one's own research. And there was a very strong sense of camaraderie, lots of socializing, drinking in the Queen's Arms, endless stories, which, if we were all here physically together, we could chat about. But it's not appropriate now to talk about that. So in the last half of my presentation, I'd like to talk about the three research themes that I've briefly outlined and discuss how they influence the wider field and particularly my own research. So let's first talk about numerical models of convection in the atmosphere and the ocean. Now, the numerical side of the numerical models of convection that Martin Miller was working on went back to his PhD thesis with Bob Pierce. And the clever thing that Martin was doing was that he showed how a non-hydrostatic model could be developed with pressure as a vertical coordinate. And, you know, pressure's a natural coordinate in the hydrostatic limit, but Martin showed how non-hydrostatic models could be formulated in pressure coordinates. And this had two important bodies of work stemmed from this. The first was the formulation of numerical weather prediction models that had been traditionally hydrostatic, shallow atmosphere models, but with Martin showing the way, people like Andy White, Rob Bromley, for example, showed how dynamically consistent quasi-hydrostatic equations could be formulated for global models with a complete representation of the Coriolis force. And talking with Andy, you know, he very clearly sees this as going back to the work that Martin was doing in the 70s at Imperial College. The second piece of work that Martin's work influenced was the formulation of non-hydrostatic ocean models. And this is work that I was involved in. So what Martin did was he soundproofed his atmospheric model, got rid of the acoustic waves by devising a formulation in pressure coordinate that was isomorphic with the equations that govern the model of an incompressible fluid. In other words, he made div V equals 0 in pressure coordinates. So he was simulating a fluid like the ocean. You could think, I knew as a graduate student that with the same model, I could study ocean convection, for example. And so with the help of Roger Bruges, we flipped Martin's model on its head, changed the equation of state, and began to study open ocean deep convection. And this picture here on the right shows a chimney, a convecting region in the ocean being driven by a patch of cooling, and there's a mix of upright convection and baroclinic instability happening. So this led to the development of what's known now as the MIT GCM, widely used ocean model, but it began its life as Miller's convection model. So the second broad area of work was parameterizing eddies in the atmosphere and ocean, moving on from Green 1970, and it was a great intellectual challenge, because parameterization really tells you to think about what the role of the parameterized scales are doing, and Green was thinking about their role in mixing potential vorticity. But in the atmosphere, there was no kind of practical need for doing this. One could readily integrate atmospheric models forward for hundreds, thousands of years, resolving the weather systems. But the same is not true of the ocean. So parametrically, the ocean is much more like Jupiter than Earth's atmosphere. You've got the deformation radius in the ocean is 10, 20 kilometers. The basin scale are thousands of kilometers. So you basically have hundreds of eddy diameters wide. Parametrically, it's more like Jupiter. And so even today, there's an urgent need to parameterize eddies in large-scale ocean models, particularly the kind of models that are used in climate change research. So in the subsequent years, myself, Jeff Vallis, applied these ideas that we learned as grad students at Imperial College. So one example of this is the ED growth rate. So you compute you can here's a map of the eddy growth rate in inverse days, inferred by mapping out the large-scale Richardson number from hydrographic data. And this is using formulae that were written down in green on going back to eddy. And you see that we pick out the Kuroshio, the Gulf Stream, Antarctic Circumpolar Current. In the red areas are places where the eddies are growing vigorously. And so if you know something about the physical scale of the eddies and the growth rate, then you can infer a mixing coefficient for potential vorticity. And these ideas are now widely used in ocean circulation models employed in climate change studies. And they go back to the work that Green was doing, we were doing as grad students. So this also led to studies of the eddy-driven theories of ocean circulation. So this is illustrated here in a channel model of the Southern Ocean. So you've got winds blowing over the ocean. Antarctica is on the left, and middle latitudes on the right. So what's going on here is that the wind through Ekman pumping tilts up the isopycnal surfaces and generates creates a store of potential energy. And then this is released by baroclinic instability, which flattens them out. So you can think of this as a competition between the Eulerian mean overturning circulation, psi bar here, and which is upending the isopycnal surface, and the eddy-induced circulation, psi star, which is driven by eddy processes, the eddy processes that we were parameterizing in the atmosphere, but here apply to the ocean. And the residual of these two overturning circulations is directed along sloping isopycnals, the residual flow in the bottom right-hand side. So if you put a tracer into the ocean, as we did say in the Dimes experiment a few years ago, where a deliberate tracer release occurred, the tracer moves up and down isentropic surfaces. And so this is how, thinking about what Frank Ludlum was telling us in classes in the 1970s, this is how the ocean basically gets water from mid depths back up to the surface. It slides it adiabatically along sloping isopycnal surfaces. Let's move on to the third project that was going on. So this shows on atmospheric blocking, this shows a block, but through the eyes of potential vorticity. And this is the Ertel PV on a 320 surface. And you could imagine kind of surfing underneath that kind of wave there. You see this large-scale undulation of the potential vorticity contours and PV mixing. And this is the work that Ludovica Illeri and Glenn Schutz did at Imperial in the 70s and 80s. And I think that their work significantly accelerated the kind of PV thinking conceptual framework that was highlighted in Huskins, McIntyre, and Robertson's famous paper on PV thinking. So this is really bringing PV back to synoptic meteorology. Now, Glenn Schutz developed a beautiful eddy straining framework for thinking about this, in which he imagined synoptic eddies being strained in this split jet. And that straining led to energy going from the eddies upscale into the mean flow, into the split. Or in terms of PV mixing ideas, the irreversible deformation of the PV contours and the mixing led to a southwards eddy PV flux, which split the jet. So all of this great science was going on in the 70s, late 70s. But having said that, and as has been alluded to earlier on in Joanna's presentation, the group was adrift a little bit in terms of leadership within physics. John Green was the de facto head of the group, but that's not what he wanted to do. And this led to atmospheric physics joining with space physics. And the best way of illustrating this is one that I remember is one occasion which I vividly remember was that I was standing with John. I was with John in his office. We were drawing on the blackboard and talking science, and the mail arrived in his office. And this is early 1980. In those days, it was real mail. There wasn't email. And John, head of department, he just threw it in the bin. He just threw the mail straight in the bin. He didn't bother reading it. He'd just had enough of it, I think, at that time. And so the group imploded. Mitch and Martin moved on to great careers elsewhere. Mitch to NCAR in the US, Martin to ECMWF. I went to do a postdoc with David Anderson at Oxford. But amongst the wreckage, there's always opportunities. And in 1982, a faculty position came up. I applied and was appointed back to the old physics department where I was an undergraduate and graduate student. And this was shortly thereafter, I joined the space physics group, and the group became known as the Space and Atmospheric Physics Group. And this was led by Professor David Southwood. And this represented a new era and new opportunities that we're going to hear about later on today. So David was a great guy. I have a lot of time for that. He did great science on the Earth's magnetosphere, magnetic reconnections. He was a skilled leader. He knew how to treat people, get the best out of them, and understood what we needed. He helped foster new directions. Ultimately, he became head of physics and went on to as head of research at the European Space Agency. So Helen Brindle is going to update us on bringing space into atmospheric physics at Imperial. So I became a lecturer in 1982 and stayed working at Imperial College until I joined MIT in 1991. These were great days, and unfortunately, and I don't have time to talk about them, but I worked with so many people in that decade, and I think we did some good stuff. In Joanna Haig also, through a circuitous route, joined physics in 1984, and as I said, became head of physics.
John, we're being time.
Yep. So ongoing collaborations. So the undergraduate exchange between Imperial College and MIT is ongoing. I love this collaboration. In the past years, I've been working with 3 Imperial undergraduates and the great students. Let's keep the collaboration between Imperial College and MIT going. And acknowledgements to Ken Bignall, Joe Haig, Andy White, etc. for enjoyable discussions in preparing this presentation. Okay, thank you very much.
Thank you. Thank you very much, John. So I think we are all deserving of a little break. I don't see any immediate questions for John on the list, so I suggest we reconvene. The break's going to be a bit shorter than we'd hoped, but we'll reconvene in 5 minutes, so at 1:30, and then we've got a final 2 talks. So thank you again to the 3 speakers we've had so far. I'll do a clap because none of us can hear, but maybe if you worked out how the icon works, you can You can do a little clap. Oh yes, they're coming in. So so we'd have over 100 people here, so that's great. So thank you very much, and we'll talk to you again in 5 minutes time. So have a quick break. Thank you. Lots of claps still coming in. Thank you, John.
Oh, thank you very much. Can you hear me?
I can.
Ah, good. Sorry, I went on a bit long.
No worries. No worries.
I didn't see. I collapsed you, and so I didn't see. Well,
I was waving.
Waving. Yeah.
Don't worry. It's great talk. Okay, Ed.
Okay, does that work? I hope you can hear me.
You've got some big shoes to fill here. So I propose we're ready to restart.
Okay, great.
So now we have 2 speakers from current members in the group. So the first one to give us a brief history of cloud physics is Ed. So Ed, please go ahead.
Cool, thank you, Ralph. So I'm going to have to say at the start, I've been at Imperial for a lot less time than the other speakers. Apologies for the necessarily abridged history here, and for anyone I've missed out. If there are things I should add, it'd be great if you could let me know at the end, because it'd be nice to build some kind of more comprehensive history of this at Imperial. But anyway, now to begin and to move on to a brief history of cloud physics and Imperial's part within it. So if we're thinking of cloud physics, we could start with Aristotle, who's probably one of the first cloud physicists. He didn't go to Imperial, but he did perform some early kind of theoretical study and observational studies of clouds, noting that they didn't really form in the upper atmosphere. They stuck around much closer to the surface, but you might expect them to form higher up because it's colder there. So there was already this kind of link between clouds forming when air gets colder. Now, he was clearly limited by the understanding of the time. He notes that clouds might not be formed there because the air was full of fire rather than just air, which is a little bit different to how we think about things today. The next big, or one of the next big changes would come with Luke Howard, who noted that if meteorologists were to be able to compare their results to other people, they'd have to have some kind of way of describing what they were seeing with clouds. And he came up with these names that we use today, cumulus, cirrus, which enabled the study of clouds in a more systematic fashion. Throughout the kind of 19th century, there was a lot of work done which relates to the thermodynamics of cloud formation. So what happens when you cool air and how does water condense in the atmosphere? So Franklin had noted that air rises when it's heated, and Erasmus Darwin, among others, including Lord Kelvin, had noted that when air expands, it cools, and that can allow water vapor to condense and form a cloud. And so it was relatively well established that clouds would form when you cooled air, but the microscopic cloud properties, particularly what caused a cloud to rain, were much less well understood at this point. So as we move into this period, the question then is, well, what do we know about them? So Luke Howard thought clouds were likely formed of bubbles as they were suspended in the atmosphere. And it was around the middle of the 19th century, Wöhler in particular showed that fog particles, when observed under a microscope, had no internal cavity. So they must be droplets. And they didn't burst when they hit things. This was expanded on further. So Aitken noted that cloud droplets need dust or an aerosol particle in order to form. So it wasn't enough just to cool the air, you needed something for those droplets to form onto. As we shift over to ice, a lot of the kind of understanding of this changed at the beginning of the 20th century. So Wegener noted that the existence of ice and liquid below 0 degrees is unstable. So water would exist along the red line in this plot. But as soon as you can form ice, you're way over 100% saturation. So the ice crystals will grow and the water droplets will shrink if you're below 0 degrees and start with supercooled water. Tor Bergeron noted then that when it was below 0 degrees, he didn't find fog in his local forest, suggesting that the trees were producing something that allowed the ice crystals to form and would switch from this liquid phase to ice phase, which then fell out of the atmosphere. And Walter Findeisen noted then that this might be the occurrence of almost every precipitation event, that if it can form some precipitation, that's a clear way in which clouds could start to rain, and that maybe every precipitation event is caused by, in the atmosphere, is caused by ice crystals. So this is where we were about the start of 1940 in terms of our basic understanding of clouds and cloud physics. And a lot of things started to change in the 1940s. So for example, there were regular aircraft flights to study the atmosphere, and these would often fly through clouds. And these began to corroborate some measurements and anecdotal evidence from India that clouds could rain even if there was no ice in them. So this Wegener, Bergeron, Findeisen process for forming precipitation couldn't explain everything about how clouds and precipitation behaved. There was also the radar detection of precipitation from the early 1940s onwards, which enabled the study of clouds and precipitation over a much larger region and began to start the development of kind of cloud physics as we might recognize it today. Now, it was about this time that 3 new lecturers were appointed at Imperial, continuing on some of the work that had been done before. John Mason arrived in 1948 and Richard Scorer in 1950. Frank Ludlum arrived originally as a Lever Hume Research Fellow from the Met Office and became a lecturer in 1951. And together, these 3 were very important in our kind of understanding of clouds and of cloud physics at Imperial. So obviously, one of the first questions they were concentrating on was this idea of forming precipitation. So given that clouds had been observed to rain without ice in them, how could you do that? This equation here is known as the Mason equation for condensational growth. The important part of it here is that the drB dt, the growth rate, slows down as the droplet radius increases. So the growth rate is very quick for small droplets, but slows down as you get to larger ones. And what this means is you can't get from a cloud droplet size, these 10 micron clouds, to the size of a rain droplet, about 1 millimeter, in an atmospherically relevant time. The condensational growth is too slow for that. In the late 40s, Irving Langmuir in the US had noted that droplets could coalesce, and that might be a way of forming rain. But he suggested it perhaps wasn't important on an atmospherically relevant timescale. Frank Ludlum's early work in 1951 showed that actually you could generate coalescence. You could generate precipitation from coalescence in warm clouds, but it required an initial size of droplet more like 20 microns. So instead of having to go from 10 microns to 1 millimeter, you now only have to make that jump from 10 to 20 microns. And John Mason noted that one of the ways you could do this might be through turbulence, that it allows some droplets to live a little bit longer in the cloud, and so you could generate precipitation that way. So the studies of warm rain were important, but there was also quite a significant focus on ice processes. So this is some of the work that John Mason is well known for. One of the first papers he wrote when he arrived at Imperial, following his original PhD studies in surface physics, was to look at ice nucleating processes, and noted that you would expect different ice nucleation processes as a function of temperature. Very cold temperatures, you might get different processes, and different types of particles could help form ice crystals. His experimental work with John Hallett produced this plot here, noting that ice crystal shape is largely a function of temperature. So you can see on this different areas marked out as a function of temperature and as a function of saturation or relative humidity. And you note here that these different areas are different shapes or different habits of ice crystals. Now this plot seems to have appeared in pretty much every textbook on cloud physics since that time. Even the most recent one I can find has a version of it in as well. So it's clearly a useful plot for understanding how ice crystals work. They also were interested in cloud electrification, coming up with a set of criteria that you'd have to fulfill for a cloud of electrification theory. And then Latham and Mason, in their work in the early 60s, came up with the temperature gradient process for charge generation. Now, this is not considered so important for cloud of electrification today, but was a really key piece of work showing how lab-based work could impact our understanding of the real atmosphere. There was also a shift more towards hailstones and storm dynamics. So Frank Ludlum noted that hailstones themselves would accrete supercooled water too quickly to freeze it. So you end up with this kind of mushy layer around the edge of the hailstone. And Keith Browning kind of built on this, explaining how this could generate a kind of a layered structure within hailstones. And you can now see a bit here of a shift more from the kind of microphysics, the droplets and the crystals, towards a relationship to the dynamics that can generate these layered structures of hailstones. So there should be a short video here. I think someone else has to display it. So this dynamics is something that I'm working on, showing these kind of time-lapse videos from the time to the 1960s. And there were a couple of quotes I really liked about this. One from John Green quoting Frank Ludlum, saying, well, the microphysics just arranged itself to make the dynamics happen. But the dynamics was the key thing about these clouds. And the second one, one which kind of follows on, the following part of the talk kind of goes along with, is the first stage in any study, and perhaps the most appealing, is one of exploration, ascertaining what actually happens. And that was a key part of this work, observing these clouds to see what would change, see what their properties were, and what controlled them. So there'd been kind of various ideas about forms of convection, but one of the things to note here is that these are all essentially two-dimensional. They're kind of a cross-section through the storm, trying to explain how the updrafts and downdrafts work and where the rain comes from. But they were all limited by a lack of observations. Usually for each of these, there are only a few sites available, which made it difficult to produce a model which was kind of more applicable. After visits to Italy and Sweden, Ludlum set out to study a large storm in the UK. Now, this is the kind of classic one that many of us will have seen before, which has become known as the Wokkingdom Storm. So the observing period in 1959 had quite a large amount of preparations for it. So there were 5 radars at East Hill near Dunstable. So one's from the Radar Research Establishment and from the US, together with David Atlas, and over 2,000 observers across the southern UK at a scale that's be difficult to replicate even today. So not only were there kind of amazing preparations for this, but the thing that always gets me is that they were really lucky as well. So the storm was particularly intense. They got 5-centimeter hail and over an inch of rain over Wokkingdom, why it's called the Wokkingdom Storm. And they were also very lucky that the storm traveled directly towards the radars, which had been calibrated the day before. And that meant that some of these features of the storm were visible when otherwise they wouldn't have been. So the echo-free vault where the updraft enters, the main updraft enters the cloud, and the wall where the significant amount of hail falls down through the cloud were particularly clearly visible on this radar cross-section on the left here, but might not have been if the storm was traveling in a different direction. Now, this Wokkingdom Storm is the first identified supercell storm. It's a very early 3D model of a traveling storm in an approximately steady state. And the steady state part is great, right? Because it means you can ignore all the d by dt terms. It makes the maths a lot simpler. One of the key things here about it was that it required wind shear to work. And it moves at an angle to the wind. So you can see the anvil at the top here. This spreads out at an angle to the wind. So having done a lot of these observations, one of the next key things would be to try and simulate them and to include it in a numerical model. And here we move on a little bit to the 1970s and the 1980s. Now, Robert Pierce had arrived from Dundee as a lecturer, and with his work with Martin Miller, who was a PhD student at the time, they built one of the first 3D cloud models. So it's not quite, as far as I can see, it's not quite the first 3D cloud model, but it's likely the first 3D deep convective cloud model. Now, because the computers at the time were limited, they had to make a few simplifications. There's no ice, it's very simple microphysics, and only has 15 by 15 by 7 grid points, which means it has almost as many edge points as it does center points, and use the whole computer at the University of London Computing Centre. But it shows the important features of the cloud field. You've got a leading updraft, downdraft, and a cold pool. Following work then combined these numerical models with theoretical understanding. Particularly, as John mentioned earlier, this idea about traveling cumulonimbus in the tropics. And one of the things I really liked about this was the version of this paper in the SPAT library has this phrase underneath. Note to be topologically possible, the flow in the interior must be of a three-dimensional nature, which is something that was really key for these studies, that you couldn't simulate them just in 2 dimensions. It also led to the development of the idea of CAPE, convective available potential energy, which is something that we use quite a lot today. And there was a matching of these in with observations as well, particularly the Wimhex experiment in the early 1970s. The next kind of thing you might say was, well, now we've got these cloud models, how could we use them to support larger scale models? So at the time, in the 1960s and 70s, it was about the time of the first global climate models. So Manabe and Smagorinsky at GFDL had built their model in 1965, and it was necessary to determine the contributions of cumulus to heating and water transport, and how you could predict those from the large-scale properties. Now, it was shown that cumulative parameterizations were very important for the climate. The original GFDL model just did a simple convective adjustment, and many people have been working on these convective parameterizations, particularly looking at cumulus fields. These early parameterizations were often developed from theoretical considerations, as there was less observational data available. But one of the key things that you could do with a numerical model is you could look at those properties in the numerical model and see how the parameterization was reflected with that. And so as cloud models increased in sophistication, both in the both increase in resolution and the time you could run them for, you begin to see studies more like this one by Gregory and Miller, which show a field of clouds rather than just a single one. About this kind of time, the 1980s or so, as John mentioned, various people were leaving the department. Mitch Moncrief had moved to NCAR in the mid-80s, Bob Pearce to Reading, and John Green to UEA in 1986. And by the time this paper was published, both Miller and Gregory had left the department as well, to ECMWF and the Met Office respectively. But it's not quite the end of the story on cloud dynamics at Imperial. Arriving at Imperial in 1994 from the chemistry group in Cambridge, Ralph Toomey's group today studies dynamics of tropical cyclones, something which kind of links back to these earlier studies in the department. Now, I didn't really talk very much about Richard Scorer during this, and he was important in these studies of clouds, developing, for example, the bubble model of convection. But one of the things that I find particularly interesting is his kind of use and championing of using satellite data for studying clouds. Now, I talk here about ship tracks, which are cloud formations generated when ships sail underneath cloud. And ships burn a very dirty fuel, which releases a lot of aerosol into the cloud and modifies the properties of the cloud. These had been observed in the 1960s, but Scorer was one of the first people to try and build a climatology of these cloud formations, looking over 5 years of AVHRR data and discovering 46 of these linear cloud formations, these ship tracks. It's a really great paper because he's shown a lot of these formations and properties of these formations, particularly these dark bands along the edge, which have been rediscovered essentially 20 years later. So he was already ahead of his time in that. We redid a similar study in the last few years and found quite a few more ship tracks. So you can see here that instead of finding just 5 a year, we find many thousands per year, partly because the improvement in satellite technology since the time gives us more coverage and a higher resolution in order to better spot these. And that just about brings us up to the present day. One of the things about Imperial is that because a lot of this work was very early on, it's had quite an impact in the field of meteorology as a whole. So this plot here shows PhDs in meteorology over the 20th century from a database held at the University of Florida. And you can see here how important some members of Imperial were just in the impact they've had in the future, particularly in cloud physics. So if we add John Mason in here, you can see all of these PhDs were supervised him or supervised by his students. And that has quite a big impact, partly because of the students he supervised. So here's John Latham and the University of Manchester group, and Peter Hobbs, kind of an orangey colour there, and his students, Zev Levin, Israeli cloud physics. Similarly, we've got Frank Ludlum here in green, Eric Eady, student John Green had a pretty strong influence on meteorology as well. And Richard Scorer is over here in purple. Now, one of the things I'd say is that Imperial's somewhat underrepresented in this database. It'd be quite nice to kind of add in some of the ones that are missing. But I think it quite nicely shows the important contribution Imperial has had to meteorology and cloud physics over the last 100 years. Thank you. If there are any questions, I'd be happy to take them, or you can email me later. I think you're muted, Ralph.
Thank you for pointing out the muting. So great. Whoa, suddenly we had two questions. It was all quiet and then it was all... So first question, how do ship tracks affect the climate around the UK and Europe?
Well, so the ship tracks themselves have a relatively small effect. So it looks like there are a lot of them there, but they're all actually pretty small. So their kind of individual effect on the climate is pretty small, but they're quite important. We use them a lot for today for understanding how aerosols, these small particulates, affect clouds.
Thank you. And then
this plot has no x-axis. It's just to separate the dots a little bit. It's not so exciting, I'm afraid.
But maybe just to explain, so that it's different people are different lines of...
Yes, yeah. So the different colours are the kind of descendants of different people at Imperial.
With the various PhD. So
yeah.
the date of their PhDs? Or?
Yeah, so that's the date of their PhDs. As I say, they're somewhat underrepresented at Imperial, particularly compared to some of the American schools, like MIT, loads of people, but it is a bigger school, I suppose. Absolutely.
Okay, so we got one other question here. Where does attempts like look at buoyancy and formation of clouds? So a question about buoyancy.
Yeah, so
experiments.
So I did have a slide on the various ideas about convection, particularly the bubble model. So Scorer and Ludlum had worked on that a bit in the early 1950s. Unfortunately, I had to get rid of it for time. I don't think it's no longer on the end here. But there was some work at Imperial on that, particularly experimental work. So kind of dropping salt, for example, into water tanks to kind of observe convection upside down in the early 1950s at Imperial. But yeah, it's one of the many things, unfortunately, I had to cut for time.
Yes, I'm sure everybody's cut out various people, and certain people keep coming up. So thank you. So if there are I don't see any further questions, then we're well on time. And so I'll hand over to Helen as our last speaker. So thank you, Ed, and over to you, Helen, about space.
Thanks, Ralph. Can everyone hear me okay? If I hear nothing, I'll assume it's okay. So yeah, it seems quite tricky to follow on from such excellent talks so far. I'm going to try and capture the last, I guess, 20 to 30 years within the group, but with a particular focus on space-related activity. So it's not going to cover everything, and like everyone else, I'm going to miss a few people out, for which I apologise. And if I do miss anything particularly important out, then please, again, like Ed said, get in touch so we can correct these records. For those of you who don't know me, I've been at Imperial since 1994 and haven't quite managed to leave yet. Worked my way through from doing a PhD here to now being a permanent member of academic staff. So I wanted to say, first of all, repeating something that John mentioned, we had obviously the atmospheric physics group, and then became amalgamated into space physics to become space and atmospheric physics. So actually the title of this talk was a bit the wrong way around. We're not really bringing space into atmospheric physics, we're really bringing atmospheric physics into space physics. And as John said, David Southwood was a particularly important player in making that happen. But actually from the beginning of the satellite age, which is sort of around that time, 1979 onwards, for operational satellite observations, researchers at Imperial were actually using these new tools quite intensively to have a look to see how well they matched their theories of cloud formation that Ed has just been telling you all about, and particularly Richard Scorer. So there's a nice piece in Ken Bignall's history which mentions that every time some new satellite imagery was available at the Dundee receiving station, Richard used to dash up there to try and get hold of the pictures and try and find something interesting in them to tell everybody about in terms of what he was seeing, and these beautiful new observations that gave much greater spatial and temporal coverage than was possible before. So in the couple of images you can see here, you can see some really beautiful example of cloud streets over Ireland from some visible imagery taken in 1979. And if you knew the weather conditions at this point, there was actually an anticyclone sitting over the mainland UK, southerly winds. And you can actually see some of the cloud streets developing into more cumulus cloud towards the west of Ireland and actually over the mountainous regions south of Dublin. And then on the right-hand image here, you can actually see something that Ed was talking about just now. So this is one of his Scorer's images of a ship track of the west coast of Portugal, and these were some of the images that he would have used to build up his climatology that Ed is now sort of, his work is building on that heritage. And for those of you who don't know, I just thought I'd highlight that if you don't know this book, you should go and find it immediately if you're interested in clouds, because it's absolutely beautiful. And apparently, according to Amazon, it's also very, very good too. So let's hope those reviewers are real reviewers. Yeah, go and have a look at some of the imagery in there. It's full of beautiful photos and explanations, and also some of this satellite imagery in some of the more recent editions. So clouds are obviously one phenomenon of interest, but they weren't the only ones. So another area of work that, again, Richard Scorer was involved in, and Brian alluded to this, was looking at pollution. And actually, he set up the first research group on air pollution dedicated solely to that in the UK, and actually contributed to drafting the British Clean Air Act in 1956. According to Wikipedia. You should never look at Wikipedia, I tell my students, but I find myself falling into that trap for that, so I hope that date is right. But later on, obviously, from satellite imagery, you could start to actually look at these pollution plumes at, again, a greater spatial and temporal scale. And here on the left, you're seeing an image of some power stations in East Germany, in this case, identified in a near-infrared channel. But he did much more than just look at these ones. There are many, many papers out there that you can go and look to see what he was doing in terms of trying to exploit the benefits of different spectral channels. So this particular one was particularly good for identifying these events when there was snow cover on the ground. Moving not very seamlessly, but trying to move seamlessly into the more recent past, there was also lots of work done by Joe that you might not be aware of, looking at trying to separate out things like air pollution so that you could see the surface signals from satellite imagery. And in particular, her team of postdocs and PhD students in the early to late 90s were developing schemes to look at atmospheric correction. So that's essentially trying to get rid of the effects of the atmosphere from the surface signal for things like ocean color. So looking at the signature of the ocean, for things like land surface temperature, particularly lake temperature, and also as a kind of byproduct deriving the actual aerosol optical thickness. And you can see some names here that you might recognize. So Peter Land, who was one of Joe's PhD students, I think is now working at the Plymouth Marine Laboratory. And you might also notice Martin Worcester there, who's now a professor at King's College London. And I've just given an example of one of the papers that she worked on with Peter, which was looking at measurements from CWIFS, which was an ocean color sensor. And you can see the effects in this graph of increasing sediment concentration on the radiance that you would expect to see as a function of wavelength at the satellite sensor. And what Peter and Joe did was develop an iterative algorithm to try and back out what the surface reflectance was, but also what the aerosol optical depth was in the atmosphere in these measurements by developing a scattering model, which took into account particulate concentrations in the ocean. And if you look at these plots, what you can see is the solid lines, which are the actual measurements against the values that they managed to retrieve, which are the crosses. Actually, you can see that this seems to be doing quite well, and it's still a well-cited paper now. So these sort of techniques are still being applied. And I thought, well, you've already seen a picture of Jo as a MSci student, but I thought it was good so that I could show what she looked like when I first came to the group. So there you are, Jo. I'm sure you're very pleased to see that picture. But around this time in 1994, there was a new appointment in the group, Professor John Harries. Now, he had previously been Associate Director for the Space Science Department at the Rutherford Appleton Lab, and at the same time Director for Products and Technology at the British National Space Centre. So was very much interested in using space for climate, but also interested in developing hardware for space. So not just using the measurements that came out, but also thinking about the instruments that can make these measurements. He also had a very strong history in using aircraft measurements, particularly in the upper troposphere, lower stratosphere, limb viewing instruments, particularly to look at the chemical composition of the lower stratosphere, with an emphasis on water vapor. And he was strongly involved at the time with a NASA project called HALO, the Halogen Occultation Experiment, which basically an instrument on the upper atmospheric research satellite that looked at sunsets and sunrises from the sun to probe the limb path through the atmosphere. So could give you very high vertical resolution through particularly the stratosphere and just into the upper troposphere, particularly if there were no clouds present, with a particular emphasis on looking at the chemistry of that region, particularly species that affected ozone depletion, which was a big issue at the time, and could be used to look at dynamics and the movement of air from the upper troposphere into the stratosphere and through the stratosphere. And what you can see in some of the diagrams here at the bottom are, first of all, the sort of target chemicals that were being observed by HALO, and secondly, just a particular focus on the water vapor, pressure versus latitude cross-section type measurements that you could get from the instrument. And this is basically just a series of sunsets that you could put together in order to get this cross-sectional information. And it gives you a very beautiful picture of what the water vapor mixing ratio looks like through the lower stratosphere, upper stratosphere, and into the mesosphere, including the important region where you're going from the upper troposphere into the lower stratosphere, and how the water vapor is being transferred in that region. So, as I said, one of the principal works with HALO at Imperial, obviously there were many other studies being done with HALO in other locations, was to look at water vapor in the middle atmosphere. And I've just picked out a few highlights here. Certainly not all of them, but there's one or two. So one paper that John was very much involved in was actually validating the HALO water vapor measurements. And that's still a really important and well-cited paper now, and is used particularly for attempts now to go back in time and create reliable climatologies of data sets that are probing water vapor. And here's an example in the plot of one of the more recent ones, which is called Swoosh, which was putting together lots of different satellite instruments measuring water vapor and ozone in this case in the stratosphere and just into the upper troposphere, different instruments. And it's really important to understand the biases and the potential noise in these data so that you can make a coherent and comprehensive record for climatology. Second trend that was going on very much at this time was looking at transport mechanisms, both within the troposphere to stratosphere, thinking about how water was actually getting from the upper troposphere into the lower stratosphere, and whether the mechanisms that were being proposed at the time were being backed up in the data, and also variability then into the upper stratosphere and mesosphere. And this was work that was very much led by John's postdoc at the time, David Jackson, who I believe is still working now at the Met Office. And then a further paper that's extremely well cited was then trying to look at, there was a big question at the time of what was going on with water vapor over time in the stratosphere. And there were some trends in the stratosphere which varied a little bit with height, as you can see in the plot here. These are trends taken from HALO, with some attempts to also look at the natural variability due to things like the quasi-biennial oscillation. And what the team tried to do at Imperial was try and explain why those trends were being seen. Could it be due to the effects of methane, or was it more to do with anomalous transport into the stratosphere? And then also what the effects would be of those trends on ozone, in conjunction with colleagues in Leeds at the time, I think, it's Martin Chipperfield's group. And what they found was that actually these water vapor trends had a noticeable additional impact on ozone depletion in the upper stratosphere and additional ozone in the lower stratosphere. I mention this paper particularly because it's particularly well cited still today, but also because it involved in the authors someone who we've been popping up every so often in the talks that we've seen so far today, circled in red, looking a bit younger there, but you can see that yeah, that was Ralph. He likes to stand out always, especially with his big, I remember those orange shorts. They were a bit disconcerting if you were actually playing football at the time. And John Marshall mentioned that it was a great camaraderie in the group, and that actually continued through John, Ralph and Joe's time and moving forward. And we used to have very competitive football matches between the atmospheric side of the group and the space side of the group. And here we're trying to say that Atmos were the greatest, although I think at this time space used to regularly win these matches. If you look very carefully at this photo, you'll actually see some familiar faces, possibly with either more or less hair than they've got now. Several of the people are still in the group now. And you'll also see one or two other people that you might recognize. So in the front row there, second from left, is Alice Larkin, who's now a professor in Manchester. And second from the back, from the right at the back is Alan Gear, who's doing some great work at the European Centre for Medium Range Weather Forecasting, data assimilation group there. So the second stream that John was interested in, and I was interested that Joe was saying that not much was going to be talked about in terms of radiation. This is true in terms of perhaps radiative theory, but one thing that John was very keen on was to actually start looking at the Earth's radiation budget. And what I'm showing here is an example of the measurements that were available for the Earth's radiation budget around 18 years ago. And if you look at this, what you'll notice is that all of the measurements there are in what's called low Earth orbit, which means that they're either polar sun synchronous, so you only see the same spot on the Earth twice a day, or they would be precessing, which means you can build up a picture of the diurnal variation in the Earth's radiation budget, but that happens over time. So it's not one particular day, it's just building up different times of day, say through a month or so. And what John was interested in, and particularly also Tony Slingo at the time, was the trying to resolve this Earth's radiation budget at a higher temporal resolution. And the idea they came up with was something called the Geostationary Earth Radiation Budget, or GERB. And the idea here was to try and observe the diurnal cycle in the Earth radiation budget, and also investigate the impact of key drivers on that timescale, with a particular idea that you might be able to look at the effects of things like mesoscale convective complexes, their effects on water vapor and how that fed back onto the radiation budget. Also potentially things like sporadic dust outbreaks or biomass burning events, and how the sampling of the diurnal cycle flowed into what you would see at longer timescales. Also an idea to exploit these data for model evaluation, and particularly numerical weather prediction models. So this was a really big effort for the Atmos part of SPAT. It's quite a big construction effort involved, including getting extra premises down on level 2 of Blackett, which is the building that's connected to Huxley. It involved basically putting together a new Earth observation calibration facility. And what you can see in the pictures on the right here are the vacuum chamber on the top within that facility, And the little thing that looks a bit like a microwave oven is the first GERB instrument going into that calibration chamber. And then in the bottom plot, you can see the full chamber with the different sources attached to it, and also the optical bench. And what we did at Imperial was basically calibrate the first GERB instrument and then the subsequent 3 GERB instruments that have followed that. The project itself was managed by Rutherford Appleton Lab, and they did a fabulous job. And much of the data processing is led by a team in the Royal Meteorological Institute in Belgium, Brussels. So it's a really international effort. I'm probably going to make everyone a little bit surprised by how much this costs. So the whole effort of putting up 4 GERBs into space cost £10 million, which even with inflation is ridiculously cheap compared to how much these things would cost if you did it today. So it's a phenomenal effort. And actually all 4 GERBs, she said, touching wood right now, are still working, still in space, and you can see evidence that in the plot at the bottom, which was when we had all 4 looking at the same part of the globe at the same time. So well done, the engineers who actually made these instruments. And I've got fond memories actually of going into college, and I'm not sure they're fond actually, but I had to do a few night shifts to actually calibrate this instrument in the calibration facility. And I can tell you that it's quite interesting being in the Blackett lab at 4 o'clock in the morning. So nowadays, this is what we see. So we've now got this record that includes the GERB observations, which are now bringing in this extra dimension of having high time resolution geostationary orbit observations, at least over the Africa and Europe, and now with GERB-2 moving a little bit over into the Indian Ocean as well. So some really novel observations. And I just wanted to go through a few of the science highlights, and I don't want to go through everything because I've got time, so I'm focusing on ones at Imperial, but there are many more than this. So some of the really nice work early on was done by Joe Futtian, who was a PhD student of John's, who then moved to the States to work with Anthony Del Genio at GIS, and did some really beautiful work having a look at diagnosing cloud radiative forcing by cloud type. So this is the difference between clear sky and all sky scenes, and just having a look at what the effects of the cloud are on the outgoing radiation, both in the long wave and the short wave and the net, and what she was able to do by combining the GERB observations with imager observations from another instrument called Severi, which flew on the same platform, is identify what the radiative forcing of each cloud type was, which was quite unusual at that time, and get an idea of which clouds were causing warming observationally and which clouds were causing a cooling. And that's what you can see in the plot on the left there. And it's not necessarily terribly surprising, but it's nice to see that you get a cooling effect from your low clouds predominantly, but also mid clouds, and then a net warming from your higher ice clouds. And this is basically their long wave effect. Then if we move on, a second stream that was important from my perspective actually was looking at tracking Sahara, and again trying to look at its associated long wave, short wave and net radiative effect. Tony Slingo published a particularly nice study of a very enormous dust event in 2006, which was perhaps the first time someone had really looked at how big these events could be, tens to 100 watts per meter squared impacts instantaneously. And then I did a little bit of work with Jackie Russell and also with some of my postdocs and PhD students to extend that to look a little bit more at the climatological impact. And what you can see in the plot at the bottom there is an attempt to characterize what the net direct radiative effect of dust is, at least at a particular time slot of day and for a particular month. And what we were able to show is how that radiative effect changes as you go through the diurnal cycle from a warming at midday to more of a cooling towards the evening and in the early morning. So I wanted to move on now to talk a little bit about another strand of work that also is linked into exploiting satellite observations. So thank you, Ralph. So the idea here was to have a look not just at the broadband effect, which was done with the Earth radiation budget, but also to look at the spectral signatures of particularly climate variability and change. So the idea of looking at how the spectrum of outgoing radiation has changed with time. This started as actually PhD work for both myself and Alan, looking at operational observations from HERS and the stratospheric sounding unit. So these are the long-term operational instruments from NOAA and NASA. But then John Harries had the idea of actually comparing some very old unique measurements from an instrument called IRIS with some more recent measurements from a Japanese instrument called IMG. And what they were able to show, what he was able to show by making this comparison and also doing some simulations of what would be expected, is that you can see clear signatures of increases in specific greenhouse gases, particularly methane, but also some little signatures of carbon dioxide, and the effects of increases in a couple of the CFCs. And this was the first time this had really actually been shown from space. More recent work in the group has actually had a look to see how robust those changes are if you were trying to use them to look at feedback analysis, and has concluded actually you need a longer time series and probably more well characterized measurements. And then finally, I wanted to just say, bringing those things together, so still looking at spectral signatures, he's also very interested in exploiting the far infrared. So this is the region of the spectrum at wavelengths longer than 15 microns or shorter than 667 inverse centimeters. It's again a topic close to my heart because it was part of my original PhD, was looking at theoretically what the signatures would be in the far infrared, following on some work done by Ashok Sinha and John, and also motivated actually by some work done by Keith Shine. And what John did was commission a build of an aircraft instrument called TAFS, which would fly on the, it was actually flexible enough to fly on various different aircraft, but it's currently housed on the Facility for Atmospheric Airborne Measurements, so NERC's airborne facility, developed by Tony Kanyas, who was actually also a little bit ahead of his time, because I found a paper of his. He was in the optical group in the physics department, which was also promoting the use of unmanned airborne vehicles in 1986. So he clearly was a little bit ahead of his time in what he was suggesting. Now, what's TAFS being used for? Basically, the idea was to understand the far infrared properties of the Earth's atmosphere, and there's a very nice review paper on that by John in Reviews of Geophysics, but also for looking at water vapor spectroscopy. So there have been a few studies on this by members of the group, and I'm picking out particularly one by Paul Green here. You can see a plot of the what we would call the foreign broadened continuum coefficients as a function of wavelength in the far infrared. And Paul's measurements here, which are the black line and the black dots, are the first ones at that time, which covered the region below 245 inverse centimeters. And a little bit more has been done since then by Catherine Fox. So Paul's now NPL and Catherine's at the Met Office, so still continuing the good work in other areas. And also more recently, we've had a look at cloud radiative effects in the far infrared, first of all by Caroline Cox, who's now at RAL, but also by Richard Banchis, who's still within the group. And a new interesting area has been to try and look at the effects of surface emissivity in the far infrared, particularly important potentially in Arctic and Antarctic regions where the water vapor content of the atmosphere is very low typically, and you're able to see down to the surface in selected micro windows. So that's a sort of smorgasbord of all the things that I can think of that are of interest in terms of space hardware and what we've been doing in the group. But there are a few new opportunities that are coming along that will bring some of this work together, and it's really nice to see. It's also really nice to see how it all builds on the heritage of what's been done before. So there are two missions in particular that are upcoming ESA missions. One is called Forum, which is the Far Infrared Radiation Understanding and Monitoring. This was actually first mooted about 20 years ago, but has finally been accepted to fly as ESA's Earth Explorer 9. And the second is a project that, again, has been kicking around for some time. It tells you that a space mission never really goes away, called Truths. And this is led by NPL. So Forum will measure in the far infrared. NPL will measure in the visible UV and near infrared. slightly different perspectives on what they're trying to do. You can read them here, but essentially they'll give us a new generation of observations spectrally resolved at very high radiometric accuracy. And by putting them together with another instrument that's going to be online at that time, which is called IASI-NG, which covers the mid-infrared, we may well have, for the first time, a full picture of what's going on to the Earth's electromagnetic spectrum across the outgoing infrared and also the reflected shortwave. So it's a really exciting time. And both missions will have nominal launch dates in the mid to late 2020s. So we hope they'll be there at the same time. It gives us lots of work to do in SPAT to get ready for them. And it's going to be an exciting time for us all, I think. Thank you very much.
Thank you, Helen. So I'm not sure I thank you for finding that picture with those lovely short. Thank you. So please join me to applaud all the speakers first of all. So that was absolutely fantastic. So thank you for those great talks. Actually, one of the things we should do also is, given this is a celebration of Imperial 100 years, and clearly the speakers couldn't cover what everybody has been doing. I noticed there are many alumni here today. So really what I want you to do also is to clap for all our alumni, for all the great work they've been doing for many decades. And I think they all deserve a clap as well, because I think that's appropriate for this event. So congratulations to all of our alumni about everything they've been doing and the credit they've been to Imperial and the history of the department. So thank you. And to celebrate the alumni, we do intend to have a physical meeting one day when we can all do that at the first opportunity. So we'll be back in touch. We haven't given up on having a physical meeting where we can exchange gossip, memories, and be inspired. So the talks themselves will be published, and on the screen there you can see the vehicles. So it'll be on YouTube, the RMetS site, and we will also put it on the Imperial College on the SPAT group site. I think it's going to be a great record, and I think that's maybe one good thing that's come out of this, is that we will have a great record which we can share then with lots of people that couldn't make it today, and we can also share with many other people. So again, thank you all for coming, and I hope to see you in person at the next opportunity. So thank you again, and goodbye. Have a good Christmas and a Happy New Year.